As you guys saw in lab, when we have a system in static equilibrium, the net force, the net torque must be zero, and we can pick our axis of rotation to be anywhere we want. But there's better and worse places to pick your axis of rotation. So in this video, we're going to go through some problem-solving strategies on solving statics problems. Now, statics problems are problems where the system is under the conditions of static equilibrium. So the net force is zero, the net torque is zero, and the end of the velocity is zero. So these are fairly straightforward problems, but there's lots of stuff going on. So always, always, always draw a picture and label all your forces. You should only do that always. Okay. Also, write the equations for the conditions of equilibrium. So remember, the net force must equal zero and the net torque must equal zero. And you would do well to remember that torque is equal to force times lever arm. So keep that one in mind. Choose an axis of rotation that simplifies the math. We're going to see in a problem here in a minute that if I have a force exerted here and another force exerted here, and there's an object sitting here, it makes sense to put my axis of rotation where I don't know a force. So if I don't know this force, it's good to put my axis of rotation there because then its lever arm is zero and its torque is therefore also zero, and I can eliminate that from this equation where my net torque has to be zero. And also be careful with sign. You'll have clockwise torques and counterclockwise torques, and you'll have positive forces and negative forces. So just keep track of everything that's going on. So here's an example problem. A 2.4 meter long, 150 kilogram uniform diving platform is supported at one end and 1 meter from the same end. A 65 kilogram diver stands on the opposite end. Determine the force exerted by each support. So like I said, always draw a picture. Now this says 2.4 meter long, 150 kilogram uniform diving platform. That tells me that the center of mass is in the center of the platform. So right in the middle of this thing, I'm going to go ahead and label the force from its own weight. And so this is 150 times 9.8. That's the force acting at the center of mass. Now there's also a support right here. I don't know how much force it exerts. So I'm going to call this force from the first support, or F1, and I don't know which direction it's going either. And then I've got my other support, and it's right here, right? Because this is 1 meter from the end. And so somewhere in here I'm going to have my force F2 as well. And so these are my two positions, and I'm going to have two forces there. Now I'm going to draw vectors in a second. I'm going to label some distances. The distance from here to here is 1 meter. And the distance all the way from the beginning to the center is 1.2 meters. And then I have a 65 kilogram diver who's over here, 65 kilograms. And so there's this downward force over here, 65 times 9.8. And this whole distance is 2.4 meters. So there's a force or a diagram that shows me where the forces are going to act. There's going to be a force from this support. There's going to be a force from this support. There's the force at the center of gravity from the plank, and there's a force from the diver's weight. So there's all my forces. So if I write the force conditions of equilibrium, what I have is F1 plus F2 plus 150 times 9.8 plus 65 times 9.8 has to equal 0. Now I'm going to go ahead and put negative in front of these because I know that they're down, and I might end up changing those signs after I pick my axis of rotation. Now I'm going to pick my axis of rotation to be right here. I don't know how big F2 is, but if I do pick that axis of rotation, it's easy for me to see that this side wants to rotate down and this side wants to rotate up. And so that must mean in order to prevent this side from rotating up, F1 must be down, and that means the only thing that has an upward force is F2. So I'm going to go ahead and say negative F1 plus F2 minus 150 times 9.8 plus 65 times 9.8 is equal to 0. That is the force conditions of equilibrium. The net torque must also be 0. Well, the net torque is due to these forces that actually have lever arms. So if I picked my axis of rotation to be here, I'm going to relabel my lever arms using the distances from the lever arm. Remember, distance from the lever arm, or distance from the axis of rotation, is lever arm. So this distance is 1 meter, this distance is 0.2 meters, and this distance is 1.4 meters. So now I can use my torque conditions to find the net torque. So clockwise, I'm going to go ahead and call positive. So clockwise, torque positive, counterclockwise, I'm going to call negative. So let's find the net torque. The net torque is equal to 65 times 9.8 times 1.4, that's force times lever arm, plus 150 times 9.8 times 0.2, that's force times lever arm, minus F1 times its lever arm, 1 meter. And this is equal to 0. Now I can go ahead and actually do the math, and I can see right away that it's going to be very easy to get F1. F1 is just equal to 65 times 9.8 times 1.4 plus 150 times 9.8 times 2. And if we let our calculator do some math for us, then what we get is F1 is equal to 891.8 plus 294, and I technically have to divide all this by 1, but dividing by 1 doesn't do a whole lot except make my units right. So I get 1185.1. So F1 equals 1185.1. Now I already know that that F1 is down, and I used that in both of my equations because I labeled it as negative here and I labeled it as negative here. I subtracted it in both of those cases. I could have added it and then I would have got my F1 to equal negative 1185.1, which would have told me yes, it's going down. And now I can sub that back into this equation and I can figure out what F2 is. So now that I know F1 is equal to negative 1185.1 newtons, I can find F2. So negative 1185.1 plus 150 times 9.8, negative 150 times 9.8, plus negative 65 times 9.8 has to equal negative F2. And so I have negatives everywhere, and so I can go ahead and get rid of those, and I'm going to get F2. So plus 150 times 9.8 plus 65 times 9.8, and I get 3292.1. So F2 equals 3,292.1 newtons, and that is an upward directed force. So I was able to find F2 and F1, but I needed both the torque and force conditions in order to do it. Now I could have picked my axis of rotation to be here, but it would have made this messy because I would have had 2 unknown torques and 2 unknown forces, and that's not so much fun. So pick a good axis of rotation and keep track of your sign.